You see, when we do this one here.
So,
Oh, okay.
sodium
Na.
plus, your nitrate is
NO3.
minus.
Mm-hmm.
So your sodium nitrate would be NaNO3. Magnesium,
Mg2 plus.
Mg. That's my
2 plus.
and your nitrate,
Oh, that's right. That's right.
And
NO3.
minus.
you need how many of
We
these?
need
Two of
two.
them.
2.
Yes.
So NO3 parentheses.
Then use your parentheses.
Now, what is that? Okay, so on the test, what is that going to be called? Name to formula? Okay.
So this would be name to formula.
Mhm.
If we went the other way, it'd be formula to.
Name. So it'd be magnesium nitrate. We just look at the parentheses. We don't look at any numbers. We just look at the parentheses. What's in the parentheses or
Unless, here's one. Name this one.
iron nitrate.
Yeah, iron 3.
Oh, you mean name?
Mm-hmm.
Okay,
Yeah.
so yeah, iron
3.
Roman numeral 3, nitrate.
Nitrate.
There you go. The only time you use the Roman numerals is for the transition metals that can have more than one charge.
Mhm. Now, how we know to use the Roman numeral?
You see the 3 at the
I know that, but I mean, on the test, will it say change formula into,
I would say go from formula to name.
that's it, and we just kind of, we'll just see the formula
And you can
now?
write down on your sheet like which ones have more than one charge. Or some of them I might put multiple choice.
But wouldn't like okay, say you had that problem up there. I mean, the 3 is gonna give it away that you need to write iron 3, right?
Mm-hmm. Yeah, so what would this one be?
Iron 2,
Nitrate.
nitrate.
Last thing, and then we can go over anything else that you want to. Covalent bonds.
Yeah, you didn't go over that.
Covalent bonds are going to be between nonmetals. So ionic bonds, unless you have your polyatomic, are going to be between a nonmetal and a nonmetal.
So are we talking about?
And if you look at your electronegativity values, fluorine is the most electronegative. It's 4. And this is on page 193. If you have anything that is greater than about 0.5 range and up through until you get into ionic compounds. But if you have two nonmetals, you can look at their electronegativity difference. And this is how you can figure out if it's nonpolar, covalent, or polar covalent.
Okay.
But again, your covalent bonding is going to be sharing electrons with within a bond. Between nonmetals. So an example, these are going to be the things that are on the right side. So here's an example. We have chlorine, natural chlorine, Cl2. This would be a covalent bond right here. Carbon makes covalent bonds. Carbon always makes 4 bonds. So if you look at the valence electrons for carbon and draw out its dot structure, it looks like this. So you have 1 on each side. To give this an octet, it'll want to make bonds with 4 other species, and it can double bond sometimes too, but carbon always makes, most cases, for your sake, will always make 4 bonds. Here's an example. CH4, all of these bonds are covalent. Again, it's between 2 nonmetals. Another example. HCl. This is going to be a covalent bond.
So will you have something on a test that says name if it's covalent or ionic?
And an ionic would be a metal and a non-metal.
Metal and a non-metal. So what is there anything with metal and metal? Or
There's metal-metal bonds, but not until you get to like
okay.
organometallic and inorganic chemistry, which is, if you're a chemistry major, then you'll see it, but not for your sake.
I think I might become a chemistry major.
So on your test, you give us
I like
the
it.
metal and the non-metal. You are not going to give us the middle ones.
You'll have some middle ones, but those are going to be in ionic time bonds. Because if they're metals, all of those in the middle are metals.
Correct. But they will be in ionic form.
Then there'll be
Like-
ionic bonds.
Like, now there was something that you did, it's pertaining to this.
Polar?
Yeah, I was gonna ask you about that. When they're close together, when the bonds are really, really close together, they're usually non-polar.
It's the electronegativities that really close together.
Right.
So the most electronegative atom, if you look on page 193, they have these values, electronegativity values. Fluorine has an electronegativity value of 4. Fluorine is the most electronegative atom. As you go across each row, electronegativity increases. As you go down each column, electronegativity decreases. So if you look at the periodic table and see the atoms, and if you're comparing which one is more electronegative than another one, you can look at the relationship in the periodic table of where they are arranged and how close they are to fluorine. So the closer they are to fluorine, the more electronegative they are. Now when you get to things like oxygen and chlorine, they're both 1 away, but remember it decreases as you go down. So chlorine is further down the periodic table than oxygen, so that's why it's 3.0. Oxygen is 3.5. Just if you're thinking about the relationship of fluorine. So electronegativity is the tendency of electrons to go towards an atom, how great that pull is. So fluorine is the most electronegative, so electrons are going to want to be the closest and usually reside around the fluorine. So let's look at these two examples here that we had. Let me redraw them. We have HCl and diatomic chlorine, ClCl. These are both pretty electronegative atoms, but they're the same. So their electronegativity difference is 0. So if you want to draw like kind of what's called an electron cloud around them, you can represent that. And they're going to have an equal sharing of an electrons. So the electrons at any given moment should be roughly the same around this chlorine as it is around this chlorine. So there's no pole. When you think of a pole, think of a magnet that has like a positive pole and a negative pole. So this is going to be nonpolar. So there's not going to be a pool of electrons towards one way or the other. Now if you look at hydrogen chloride, chlorine or hydrogen, which one is more electronegative? Chlorine.
Yeah.
So if we draw a similar map or cloud around this to kind of represent where the electrons would want to reside, it looks something kind of like this. You'd have a greater distribution of electrons towards the chlorine end. This is going to be polar. Now, an ionic compound